In the last lesson, we learnt a magnetic field due to a circular loop. When current flows through a circular loop, a magnetic field is produced. The magnetic field is in the form of concentric rings around the loop. In the center of the loop, we find that the field is maximum because the magnetic field lines assist one another. What would happen if many such loops are put close to one another? Field would look somewhat like this, just like that of a bar magnet. Here we have a number of coils kept close to each other, and such a structure is called a solenoid. A solenoid acts as a magnet as long as current is passing through it. And the magnetic field due to a solenoid is very similar to that of a bar magnet. Here is the field due to a bar magnet, which are closed curves, and this is a field due to a solenoid, which is also closed curves. Let us examine the nature of this field. Outside the magnet, you find that the space between the magnetic field lines is not constant. So we say the field outside the solenoid is non-uniform. However, inside the solenoid, the field lines are straight and equally spaced. So the field inside the solenoid is said to be a uniform field. So if we were to define a solenoid, it's a coil of many circular turns of insulated copper wire wrapped closely in the shape of a cylinder is called a solenoid. So here's a picture of a solenoid. Here we have these coils, circular coils that are wrapped in the form of a cylinder. This is then attached to a battery, and then current begins to flow through this circuit. And as current begins to flow to the circuit, the solenoid then acts as a magnet. Here, this is current passing through the solenoid. We'll also learn about the magnetic field due to the solenoid and the factors on which it depends. Now, this magnetic field due to a solenoid resembles that of a bar magnet. The field lines are closed curves. They emerge from one end of the coil and they merge in the other. So one end of the coil is the north pole while the other becomes the south pole. Unlike the bar magnet, the magnetic field due to a solenoid can be changed. We go ahead and learn the factors on which the field due to a solenoid depends. The first factor is it is directly proportional to the number of turns. Larger the number of turns, stronger is the field. Next, it's directly proportional to the current flowing through the conductor or the solenoid, which means more is the current, stronger is the field. So the third point is depends on the nature of the core. Now, if the core inserted here is an soft iron core, if you put a soft iron core, we find that the magnetic field increases. So here we have a soft iron core, the magnetic field gets stronger. Let's go ahead and summarize what we have learned. These are the three magnetic fields we have learned. The magnetic field due to a straight conductor, which were concentric rings. Then this was a magnetic field due to a current carrying circular loop, and this was a magnetic field due to a solenoid, which looks so much like that of a bar magnet. The next point we're going to learn is difference between a permanent magnet and that of a solenoid. So the first point of difference is a permanent magnet is permanent. It doesn't lose its magnetism unless you drop it, and a solenoid is a temporary magnet because it acts as a magnet as long as current is flowing through it. The minute the current stops flowing to it, it loses its magnetism. X is a magnet as long as current flows through it. The minute the current flows, it acts as a magnet. The current stops, it stops acting as a magnet. It loses its magnetism. Another difference is that the polarity of a bar magnet cannot be changed. If we have a bar magnet, one end will remain north while the other end will remain south. There is no change in the polarity. This one end that is north will always remain north, and the one that is south will always remain south. However, in the solenoid, we can change the polarity by changing the direction of the current. Here we have a solenoid where the current is flowing in this direction. Then we find that the field lines here are in this direction. They flow in this direction here. These two figures clearly indicate how the polarity can be changed. In the first, we find the current flowing in one direction and the magnetic fields emerge and merge here. So this becomes the north pole. This is the north and this is the south. In the next figure, the current is reversed. And when the current is reversed, now the fields have a different direction. They emerge from this end and they merge in this end. So now in this case we have this is our north and this is our south. In the earlier we had this north and this south. We changed the direction of the current. Now this became south pole and this one became the north pole. This polarity of an electromagnet can be changed by changing the direction of current. And the last is we see the strength of a permanent magnet is constant. It remains the same. But the strength of a solenoid can be changed by the different factors we learned earlier. If we pass more current, more stronger is the field. If we pass less current, weaker is the field. So I just added up here. The strength cannot be changed. And in this solenoid, the strength can be changed. We'll go ahead and see some uses of solenoids. Remember, solenoid is a temporary magnet. As long as current flows through it, it attracts other magnetic material and acts as a magnet. You stop the current flowing to it, it stops being a magnet. So it can be used in cranes, in lifting big iron sheets. It is also used in an electric bell. As soon as current flows through this bell, it will attract this gong and make a sound. It is also used in magnetic trains. There are many other uses of electromagnet. It is very widely used.